Today we are going to learn about enhancing KNN with distance metrics. We'll explore how different distance metrics can significantly impact the performance and accuracy of the k-nearest neighbors algorithm. By the end of this video, you will be equipped with the skills to select and implement the best distance metric for your specific machine learning projects. Welcome to our exploration of the fascinating world of k-nearest neighbors, often abbreviated as KNN, and the pivotal role that distance metrics play in its functionality. KNN is a simple, yet powerful, machine learning algorithm used for both classification and regression tasks. It operates on the premise that similar data points are likely found close to each other. This is where distance metrics come into play. They are mathematical formulas that measure the similarity or dissimilarity between two or more objects. The choice of distance metric can significantly influence the accuracy and performance of a KNN model. In this video, we will dive deep into various distance metrics, understanding their strengths and weaknesses, and how they can be leveraged to improve your models. Whether you're working on a classification problem in healthcare or a regression task in finance, understanding these metrics is crucial. Let's begin our journey by exploring the fundamental concepts and laying a strong foundation for the more advanced topics that follow. The Euclidean distance metric is perhaps the most intuitive and widely used among the various metrics available. It's calculated as the straight line distance between 2 points in Euclidean space. This metric works exceptionally well in low-dimensional spaces where the intuitive notion of distance aligns closely with our visual understanding. However, it has limitations. In high-dimensional spaces, a phenomenon known as the curse of dimensionality can cause the Euclidean distance to become less meaningful. Distances in high-dimensional space can become nearly uniform, reducing the effectiveness of the metric. Additionally, Euclidean distance is sensitive to the scale of the data. If your features have different units or scales, it could lead to biased results unless the data is normalized. Despite these challenges, the Euclidean distance is still very effective in many real-world applications, particularly when data is well-scaled and in a lower dimensional context. We'll delve deeper into how these strengths and weaknesses manifest in practical scenarios and how you can mitigate some of the challenges. Manhattan distance, also known as the L1 distance or taxicab distance, is another commonly used metric that calculates the total absolute differences between the coordinates of a pair of objects. Visualize it as the shortest path a taxi would take on a grid layout of city streets, hence the name. Unlike Euclidean distance, Manhattan distance is more robust in higher dimensional spaces and is less influenced by outliers due to its nature of summing absolute differences. This makes it particularly useful in scenarios where the data contains noise or outliers. It is also effective in grid-based path calculations, often used in robotics and urban planning applications. However, Manhattan distance can struggle with diagonal movements, as it doesn't consider the direct line between 2 points. This metric is particularly well suited for cases where the dimensions of the data are consistently scaled, and where grid-like structures are involved. Understanding these nuances will help you decide when to use Manhattan distance over other metrics in your KNN models.
The Minkowski distance is a versatile and generalized metric that encompasses both Euclidean and Manhattan distances as special cases. It is defined by the formula that includes a parameter p, which determines the type of distance calculated. When p equals 1, it simplifies to the Manhattan distance, and when p equals 2, it becomes the Euclidean distance. The flexibility of the Minkowski distance lies in its ability to adapt to different types of data by varying the value of p. For example, higher values of p increase the emphasis on larger differences between coordinates, which can be useful in specific scenarios. Selecting the appropriate p-value is crucial and should be based on the characteristics of your data and the problem at hand. This metric provides a powerful tool for tailoring the distance calculation to best fit the nuances of your specific dataset. As we proceed, we'll analyze how to choose the right p for your data, supported by practical examples and case studies. The Mahalanobis distance is an advanced distance metric that considers the correlations between variables in a dataset, making it highly effective for multivariate analysis. Unlike other metrics, Mahalanobis distance accounts for the variance and covariance among variables, allowing it to measure distance in a way that considers the data's inherent structure. This is particularly useful in datasets where features are correlated, as it can identify the true distance between data points in the context of this correlation. Calculating Mahalanobis distance requires the inversion of the covariance matrix, which can be computationally intensive for large datasets. However, its ability to detect outliers and anomalies in multivariate data makes it invaluable in fields like finance and biology, where understanding the underlying data structure is critical. We'll explore how this metric is implemented, its computational requirements, and real-world applications where it excels. The choice of distance metric can have a profound impact on the performance and accuracy of a KNN model. Different metrics can lead to different interpretations of which neighbors are closest, and this can significantly alter the predictions made by the algorithm. For instance, while Euclidean distance might be suitable for datasets with uniform feature scales, Manhattan distance might perform better in datasets with outliers. The accuracy of the model hinges on selecting the appropriate metric that aligns with the data's distribution and the problem's requirements. Moreover, there are trade-offs to consider. A metric that excels in one scenario might underperform in another. We'll delve into how these trade-offs manifest and discuss strategies for analyzing the impact of different metrics on your model's performance. Through examples and experiments, we'll uncover how to make informed decisions in metric selection to enhance the accuracy and reliability of your KNN models.
Cross-validation is a crucial technique in the model evaluation process, especially when assessing the impact of different distance metrics on a KNN model. It involves partitioning the data into subsets, training the model on some subsets while validating it on others, and repeating this process multiple times. This approach helps ensure that the model's performance is robust and not just a result of overfitting to a specific dataset. By applying cross-validation, you can effectively compare how different distance metrics perform under varied conditions. Techniques such as k-fold cross-validation and leave-one-out cross-validation provide a comprehensive assessment of model reliability. Implementing these in Python is straightforward with libraries like scikit-learn, which offer built-in functions to facilitate the process. We will walk through the implementation of cross-validation techniques, demonstrating how they can be used to assess the efficacy of different distance metrics in enhancing KNN models.
In some cases, the standard distance metrics may not fully capture the nuances of your specific data or problem. This is where creating custom distance functions can be highly beneficial. Custom distance metrics allow you to tailor the distance calculation to better fit the unique characteristics of your dataset. For instance, you might need a metric that gives more weight to certain features or accounts for domain-specific knowledge. Creating a custom distance function can involve modifying existing metrics or designing entirely new ones from scratch. While this approach offers flexibility and precision, it also comes with challenges, such as ensuring the metric's validity and handling increased computational complexity. We will guide you through the process of developing custom distance functions in Python, providing examples and tips to help you create metrics that enhance your KNN model's performance in specialized applications. To bring the concepts we've discussed to life, let's examine a real-world case study involving distance metric selection in a practical scenario. Consider a healthcare dataset used for predicting patient outcomes based on various health indicators. In this scenario, the choice of distance metric can significantly influence the model's predictions. We'll go through the process of analyzing the data, selecting appropriate metrics like Mahalanobis for its ability to handle correlated features, and evaluating the impact on model outcomes. This case study will highlight the importance of understanding your data's structure and the problem's context in choosing the right distance metric. Through this example, we'll extract valuable lessons and insights that can be applied to your own projects, demonstrating how thoughtful metric selection can lead to more accurate and reliable KNN models. In this segment, we'll focus on the hands-on implementation of KNN models using Python libraries such as scikit-learn. These libraries provide robust tools for implementing various distance metrics, enabling you to experiment with and optimize your models. We'll walk through code examples demonstrating how to set up a KNN model, choose different distance metrics, and evaluate their performance. We'll also discuss practical tips for optimizing your models, such as feature scaling and parameter tuning. By the end of this section, you'll be equipped with the knowledge and skills to implement KNN models in Python confidently, enhancing their performance through informed distance metric selection. Whether you're a seasoned programmer or new to machine learning, these hands-on exercises will provide you with valuable experience and insights. As we conclude our exploration of enhancing KNN with distance metrics, let's recap the key concepts we've covered. We've delved into the importance of distance metric selection and its profound impact on KNN model performance. From understanding the strengths and weaknesses of Euclidean, Manhattan, Minkowski, and Mahalanobis distances to exploring custom distance functions and real-world case studies, we've equipped you with the knowledge to make informed decisions in your projects. Remember, the choice of metric can significantly influence your model's accuracy and relevance, so don't hesitate to experiment and explore different metrics. As you continue your journey in machine learning, we encourage you to deepen your understanding of these concepts and explore additional resources to enhance your skills further. Thank you for joining us, and we wish you success in your machine learning endeavors.